Okay, so we'll be deriving the common potential form of the charge sharing between two bodies, and particularly the spherical form. So it is. So we may consider a sphere, not that. It should have been proper. So let me consider a sphere. Let me call this a sphere as A. It has a radii of, let's call this RA. That's the radius of A. And there is another sphere that is sphere B. It has a radii of RB. Right? Hope is visible to you. Nice and clear. So, what if there is a wire between them? So let me write down the topic so that you can understand what is happening. And this is charge sharing between bodies by common potential method. So this word common potential is important here. And let's say after joining them from a wire, let's say I have given a charge that is QA to this sphere, and this will distribute on this whole sphere because it is a conducting sphere. In order to make the electric field inside A equals 0, the charge QA I have given to this sphere will distribute symmetrically in all the directions. So I can say its surface charge density to the sigma A is constant, and it's just nothing but Q upon 4 pi R A squared. That's not needed. The mathematical term is just for your understanding. Right? And same for the charge for the body of the sphere B. I have given it a charge, let's say QB, and this A and B term are just down suffix which can change to R1 and R2, but it's a lot more confusing, like remembering the formula in R1 and R2 terms is just more confusing. You can just remember in RA and RB, whenever the question comes, you can just put out the values and solve it from there. Same for the surface B. The charge will distribute symmetrically in order to make the electric field inside a conducting sphere equals 0. So now what? This charge has it has a charge of QA. I can write it as QA, QA, and RA. These are three terms here and three terms there. QB, QB, and RB. You're getting my point? Okay. So let us consider a switch here. And if I ask you what is the potential of A, the sphere A, on its surface when the switch is open, you're going to say VA equals the the potential at the infinity minus this potential at the surface. So it's just going to be KQA by RA, because the charge given to the sphere is QA and the radius is QA. So it is KQ by R, that just becomes KQA by RA. Same for the sphere B. VB equals QB, KQB, KQB by RB. So these are the potential at the surfaces of these spheres. But what happens if I connect those spheres. So this just represents that the switch is closed. And these situations are before closing the switch. And I want you to think about it once, pausing the video, that what would happen to the spheres if I connect them and close the switch. Have you think about it? Just give it a thought. What will happen, like if the charge would flow here, or whether this charge will flow there? What will be the equal charges? So if I ask you a question, I'm erasing it, right? The down part. So my question is, find the final charge distribution on these spheres after closing the switch. Find the final charge distribution between A and B. So give it a thought and try this. I guess I will have to raise the upper part. So I'm just making this up again. Have you given it a thought? Okay. So let's start again. I had a sphere A. I had another sphere that is B. That is A. Fine. Initial charge is QA, and this is B. Initial charge was QB, and their radius were RA and RB respectively. So what happened is I connected them by closing the switch, and the main concept behind this is potential here. I call this point as VA, and same potential here, VB. They become equal after connecting the switch, assuming that the wires are ideal, right? So after closing the switch, let's say because of the potential will change, those potentials will become as VA equals VB equals V common. And because of the change in potential, this whole system has become an equipotential surface. And since that it has become that, the potential has changed of the whole system, but the potential will be same. And because the potential has changed from that initial potential, let me write here VA initial, VB initial equals KQA by RA, KQB by RB. So this was their initial potential, and this is some V common, which we need to find. So get this concept. This is a very important concept. I'm writing here a critical point because whenever you will forget the formula easily, and if you know the concept, you can just derive this whole equation, which I'm going to derive it. You can derive this whole equation at once. So this is V common. They will achieve after I close the switch, and what will happen is they will share some charges in order to equalize the potential and become a same whole system will behave as the same equipotential surface, because these are all conducting wires and the sphere itself is conducting. So let me write here what we know. we know that the total charge is always conserved. That is QA plus QB, isn't it? Right? And let me say that I know this concept that if I connect two equipotential surfaces, their potential will have to be the same because no two equipotential surfaces can intersect each other. So I'm just writing here like VA equals VB, and these are final potential, right? So if these are final potential, then I can write that some charge will reside on the Q, on the sphere A. Let me tell this charge as Q final, which I need to calculate, and the rest of the charge will go to that sphere. So I'm just writing it as QT minus QF. So that's how I wrote it. Like if there is some charge after the equipotential surface, if after I connect those sphere A and sphere B, their potential will become same. We call it V common, and it would be nothing but that final charge will be accumulated here because the same charge which was there in the initial state QA will not be the same. It will be some unknown variable that I call as QF, and I know that the total charge here is QT. That is, the total charge is always conserved in any situation. So in the final situation, that charge will be conserved. So I just wrote it as QT minus QF. That some charge is accumulated here and the rest of it would go here. So let me write its potential in the final state. So let me write it as Q final by RA equals KQ by R. So the final charge on B is KQT minus QF upon RB. And this is really important because we will calculate the final charge on this sphere because we know the addition of those charges like QA plus QB is just equals to QT, and we will just have one unknown variable, that is QF. So K are the same, these are just the constants. So we are just left with QT by RB and minus QF by RB. I will bring that here and write it as here. Just try to write down whatever I'm explaining because you won't get it unless you do it. And so I'm writing it as Q final by RA plus Q final by RB equals QT by RB. Is it visible to you? No, it isn't. Now it's visible to you. So I guess I will have to erase this part. So I'm just rewriting this down. I'm writing this whole thing down. So what we have is VA equals VB, that is the final state, final potential on A and B respectively, and QVA will nothing be but QF by RA equals KQT minus QF by RB. Now rearranging them and simplifying them gives us QF by RA plus of QF by RB equals QT by R. RB. So I can see that this Q final and Q final are common here, so I just get them here. So it would be nothing but Q final taking the LCM RA RB RA plus of RB equals QT by RB. Now the denominators are the same, so I can cut this RB and get rid of all those extra constant. I get this here. So this equation, I'm writing this here. So I just get the final result as Q final equals QT, and this is denominator, so I will cross multiply it. RA upon RB plus RB, and this is the final result I get. So that's how we calculate all those final charges that accumulate on the bodies of the spherical conducting spheres after I close the switch. So I will just write the general formula in the end, which you have to remember along with the concept, because you can forget this formula easily whenever someone will give you any charges or spherical bodies, and they will tell you the radii of those bodies, and they will give you the charge initially and finally whatever is a variable there. Then you can just use those formulas, and they may ask you the ratio, what is the ratio of the charges in the final and in the initial state. So they can ask you anything, but the concept is this: after connecting the switch with both the charges, this whole system becomes an equal potential surface, and this will acquire a common potential that is V common, and from V common you can derive the final charges. So I will just call the final charges on A as QAF equals QT. That's the addition of QA and QB. That were the initial charges, like QT equals QA plus of QB. This is the total charge in the system. QT times of radius of A divided by RA plus of RB. So that's the first equation. And same for the second sphere. If I have to calculate its charge distribution in the final state, it will be nothing but QT times of RA upon RA plus of RB. And there is a special case here in which these radii are equal. And so how do we do that? So let me write just a special case here. You have studied this in your previous chapter, that is electrostatics, that if we connect two identical bodies together, the charges distribute to a factor of half. And that's what these equations will prove here. So if RA equals RB, that just means their bodies are symmetrical. The charge distributions will just become, just see here, QA final. After connecting those identical spheres together, we get QT, then RA, and the denominator I can just write it as 2 times of RA. So it just becomes QT by 2, and subsequently QBF. I think you're not able to see it. So subsequently that charge distribution, which is nothing but QBF, that's just the final charge in B, will become as QT by 2. So I hope you understood it well, and I gave my full efforts to make you understand it, and hope you enjoyed the video and hope you got the concept. This is the supreme concept which you can apply anywhere. Even the charge distribution is a variable of the spheres. Okay? So, good luck. Bye.